Hello everyone. Today we will see what is Hilbert transform. Before knowing what is Hilbert transform, we will learn what is Fourier transform. Fourier transform, it is useful for evaluating the frequency content of a signal. So we can say that Fourier transform is the mathematical basis to analyze and design the frequency selective filters. And these frequency selective filters are useful for separation of the signals on the basis of frequency content. So there is another method for separating the signals based on the phase selectivity, and this technique it is known as the Hilbert transform. Therefore, Hilbert transform it provides a mathematical basis for analyzing and designing phase selective filters for separation of the signals. So these are the four stages of the Hilbert transform. That is, it will establish a theoretical foundation for signal analysis, then apply mathematical tools to understand the signal characteristics and create filters to selectively process signals and successfully isolate desired signals from the noise. So we have to always remember that the Fourier transform, it uses the frequency domain analysis, and the Hilbert transform uses the time domain analysis. Now let us see the definition of the Hilbert transform. The definition is, if the phase angle of all the components of a given signal are shifted by plus or minus 90 degrees, then the resulting function of time is the Hilbert transform of the signal. And this is the formula for Hilbert transform, that is x cap of t. X cap of t is nothing but the Hilbert transform of x of t. It is given as 1 by pi integration minus infinity to plus infinity x of tau t minus tau d tau. We'll take this as equation 1. So x cap of t is nothing but the Hilbert transform. This is the pictorial representation of the definition of the Hilbert transform. Then we have formula. Then it is represented by this notation. Okay, and it deals with the phase angle of all the components of the signal which are shifted by 90 degrees. Now to obtain x of t from x cap of t, we can use the inverse Hilbert transform, which is given by x of t is equal to minus 1 by pi integration minus infinity to plus infinity x cap of tau divide t x cap of t divided by t minus tau d tau. So we'll take this as equation 2. Now from the definition of x cap of t, convolution of the signal x of t, that is x cap of t is the convolution of x of t with the time function 1 by pi t. Okay, here x cap of t is nothing but the convolution of x of t with the time function 1 by pi t. So we can write it as x cap of t is equal to convolution of x of t and 1 by pi t. We'll take this as equation 3. Now we know that convolution in time domain is the product in the frequency domain. So for this we can write it as Fourier transform of x of t is equal to x of f, capital X of f. That is Fourier transform of x of t is capital X of f. Okay, that is, this is in time domain and this is in the frequency domain. And Fourier transform of 1 by pi t, it is given as minus j signum function of f. This SGN is nothing but the signum function, which is defined as, it will be 1 when the frequency components are greater than 0. It will be 0 for f is equal to 0, and it will be minus 1 for f less than 0. Now we have obtained the Fourier transform of x of t and 1 by pi. So we can write the Fourier transform of equation 3. Okay, equation 3 was what? This is the equation number 3. Okay, so we will write the Fourier transform of this equation, which will be given as x cap of f, capital X cap of f is equal to x of f into minus j signum function of f. Okay, so here this can be written finally as x cap of f is equal to minus of j signum function of f into x of f. So we'll take this as equation number 4. Now we can represent this equation by a two-port device where the input will be small x of t and the output will be x cap of t, that is the Hilbert transform of x of t. So here what we'll do is we will take a signal x of t. Okay, so here we are taking a signal x of n. Then we are finding the Fourier transform of this. So we'll get it as x of f. Now what we do is we will multiply this with the signum function, that is minus j signum function of f, in order to obtain the Hilbert transform of x of f. Okay. Now in order to get x cap of t, we will apply what? Inverse Fourier transform, and we'll get x cap of t, that is the Hilbert transform. Okay, that is nothing but the inverse Hilbert transform of this capital Hilbert transform of this capital X of f. Okay, so if you take Fourier transform of x of t, actually here it should be x of t, we will obtain what? Capital X of f. Now what we have done, we have multiplied this with the signum function and we will obtain x cap of f. If we take the inverse Fourier transform of x cap of f, we will get x cap of t. Okay, so this device it is known as a two-port device. So here what we have is, we'll have a phase shift of minus 90 degrees for all the positive frequencies, and we will have a phase shift of plus 90 degrees for all the negative frequencies of the input signals. Okay, so here there is just a pictorial representation of this. We are giving an input signal, we want to find out the frequency component. So there will be a minus 90 degree phase shift for positive frequencies, there will be a plus 90 degree phase shift for negative frequencies, then we'll get the output signal. This is another picture to represent this. You can refer any of these two. Now here therefore here there is a pictorial representation of the amplitude response of the signal for the Hilbert transform, where we can see the amplitude is not affected. Okay, it is not affected. So here the amplitude remains constant, and this figure, it shows the frequency response of the signal after the Hilbert transform is applied, where all the positive signals are shifted by minus 90 degree and all the negative frequencies are shifted by plus 90 degrees. Okay, so for positive frequency it is minus 90 degrees phase shift, and for negative frequencies it is plus 90 degrees phase shift. Okay, so these are some of the Hilbert transform pairs. Pairs here, this is in time domain and these are in the frequency domain. You can remember these. So if you remember these, this will be helpful in solving the problems. Then we have properties of Hilbert transform. First property is a signal g of t and its Hilbert transform g cap of t. Okay, signal is g of t. Its Hilbert transform is represented by g cap of t. These both will have the same magnitude spectrum, and it is given as magnitude of capital G of f is equal to magnitude of capital G of capital G cap of f. So here the initial signal before applying the Hilbert transform will have the same magnitude as that of the transformed signal where the phase will be altered. Then we have property 2. It is a signal g cap of t. Okay, if g cap of t is the Hilbert transform of g of t, then the Hilbert transform of g cap of t will be minus g of t. Fine. So it means that here you will be having the negative value. Okay. So original signal, positive phase of the signal will be there. Suppose we have positive phase of the signal. When you apply Hilbert transform, then the phase of the signal will be changed to negative. Then we have third property, that is a signal g of t and its Hilbert transform g cap of t are orthogonal over the entire time interval minus infinity to plus infinity. So here it can be written as integration minus infinity to plus infinity g of t into g cap of t dt is equal to 0. Okay, so here what you have, the signal g of t and its Hilbert transform are orthogonal. When you multiply this over the interval minus infinity to plus infinity, then the answer will be 0. So Hilbert transform g cap of t is orthogonal to g of t. These are some of the applications of Hilbert transform. Here you have signal processing, where it will extract the amplitude, envelope and the instantaneous frequency. Then you have communication systems, which enables the SSB single sideband modulation and analytic signal generation. Then you have control system. It is used for phase compensation without affecting the amplitude. You have medical applications, which analyzes the ECG and EEG signals for clinical insights. Then comes the radar and the sonar, where it helps in Doppler analysis and baseband signal conversion. Then you have vibration analysis, which detects the mechanical faults using the envelope detection. And you have seismology, which will extract which will extract the instantaneous attributes from the seismic signals. Okay, and here this is nothing but the Hilbert transform of a low pass signal, where we start with the low pass signal g of t, small g of t, meaning that its frequency components are limited within a range from minus w to plus w. So this can be seen in the Fourier transform of the signal, which shows its frequency spectrum. Okay, then the Fourier transform of when you apply the Hilbert transform to the signal small g of t, we will get a new signal, that is capital small g cap of t. So the Fourier transform of small g cap of t will be this one, that is capital G cap of f. This new spectrum, it has undergone a phase shift. You can see here it has undergone a phase shift. It introduces a minus 90-degree phase shift for the positive frequencies, minus 90-degree phase shift for the positive frequencies, and plus 90-degree phase shift to the negative frequencies. So as a result, while the amplitude of the frequency components remains unchanged, as per the property 1 of the Hilbert transform, the phase signal, the phase of the signal, it is radically altered. Okay, you can see the phase of this signal, it is radically altered. So what we have seen here is Hilbert transform regarding the signal components, that is there will be a change in the frequency, what happens when the frequency is positive and what happens when the frequency is negative, and the amplitude remains unchanged. So here we have seen that the Fourier transform will be always in the it uses always the frequency domain, and the Hilbert transform, it always uses the time domain. And here the phase shift will be 90-degree phase shift, that is plus or minus 90-degree phase shift. So this was about the Hilbert transform. I hope you have understood this. If you have any queries, you can comment in the comment section, and do like and subscribe my channel. Thank you.